Hello, welcome to another lecture. In this lecture, we're going to go ahead and design a connection between beam and girder. There are many different type of, few different type of connection between beam and girder. We talked about double angle before. This time, we're going to talk about end plate connection. End plate connection is basically a plate is welded to the end of the beam, and then you connect them to the girder. Let me show you what I have. I got some material I want to show you. Let's consider a beam to a girder connection. When we connect a beam to a girder, we want the flange of the beam to align with the flange of the girder at the same elevation. This alignment creates a gap between the web of the beam and the web of the girder, and you can see the gap right there. To make the connection fit properly, the steel beam should be modified with the cuts, typically at the flange and the web. This modification is usually called a coped beam. What I was talking about, this is a coped beam, and it has been coped out right here, been notched out right there. This is basically the width of the half of the flange of the girder. So when you bring this in, it will kind of, your end plate right here will touch into the web of the girder. And this is the end plate, is basically a plate welded to the end of the beam. When we look at this, I want to show you the end plate first. Let me show you that here. Look at the welding right there. There's the plate is welded to the both side of the web, and then also welded to the both bottom and top of the flange. And when we design this, connect this to a girder that has a 4 or 5 different possible failure mode, we have to examine all those up. Look up in the board and you can see one is basically, you want to check the available shear in the plate itself and see if the plate with all the holes in it with the block shear rupture will hold up. Then we're going to check the bolt connection, if the bolt's strong enough to connect the weight, the shear weight, and then we're going to connect the check the shear capacity of the web itself in this condition. Then we're going to check the because we took a notch out of the beam, now we have weakened this beam. We're going to double check the beam for that weight with the coped beam, and then we're going to connect the girder. Normally it's bigger and stronger, we don't have to connect it, we don't have to check it, but we can also check the girder web and shear connection between both of them. Okay, we're going to go ahead and work on this example. This example we have, it says the design available strength of a shear end plate connection to connect a W18 by 50 beam to a W21 by 62 girder web. So this is the drawing I did. So we have this W18 by 50 right here, and the connecting to this girder, and it's kind of coped. Based on these loads, both the girder and the beam already been designed, so we don't have to worry about it. But looking at the plan view of one of the bay, these green line being the girder, and then your beam is about 40 feet long, and it's about 10 feet spacing between beam. So the dead load is about 50 pounds per square foot, and the life load is 150 pounds per square foot. And what we want to do, we're just going to get a plate like this, ended to the welded to the end of the beam. We're going to do the next one right here. It's just like this plate right here, which I just showed you. The plate itself, let me make this a little bit bigger. So the plate right here is about 4 inches, because the girder has the flange of the girder is 8 inches. So this is 4 inch. And bring them down 2 inches, brings them up to the right elevation, because one is a W21 and the other one is W18. That will line them up pretty good. And it has 1, 2, 3 bolt hole as shown, and the plate is about 1/4 inch thick by 6 inch by 8.5. So it's 8.5 going this way and 6 inch going width-wise. And of course, the welding is on both sides, top and bottom. It's on this side and the other side also here and bottom, as I showed you on a video. To do this, we have to go through, find out what is the failure mode on this right here. And as we talked about, we're going to check for an in-plate available shear strength, and then we're going to available shear strength transfer of the bolt hole, the bolt itself, weld and beam web available strength. Okay, so first we're going to go ahead and figure out the dead load and life load per. So this is the turbo tree width is about 10 feet. Therefore, our dead load is going to be 50 times 10. That makes it 500 pound per foot. And the life load is going to be 150 times 10. And that gives me 1,500 pound per foot. So I'm going to come back down here. And dead load is 500 pound per foot, and life load is 1,500 pound per foot. So what I need is the reaction. Really, I want to know what the shear is. That's going to be my shear. We don't do this is for basically a shear connection. So this reaction is WL divided by 2. You remember that from kindergarten. And for dead load, it's going to be a 500 times 40 divided by 2, and that will give me a 10 kips dead load for shear. And life load is going to be same thing, 1,500 times 40 divided by 2. That's going to be about 30 kips. So your dead load is going to be 10 kips, and your life load is going to be 30 kips on for the shear right here. Okay, so to continue with this problem, we're going to use 70 KSI weld and a 50 KSI plate. And if you go to the manual, which we use in the 16th edition, table 2425, we can say Fy is equal 50 for all 3 pieces, and Fu is equal 65 KSI. Again, from table 1, the thickness of the beam web is 0.355, and the girder is a little bit bigger, is 0.4 inches. Then we're going to go to ASE chapter 2. You remember that in structural analysis. We're basically going to do a load combination, and we're going to say, okay, for load resistance factor design, our RU is equal 1.2 times 10 plus, that was a dead load, 1.6 times the life load, which came out to be 30 kips. And that gave me about 60 kip. Okay, now if I do the allowable stress design, which I kind of like, ASD, and that's basically going to add both of them. We're going to call it RA is equal 10 plus 30, which is equal 40 kips. If you're a designer, young designer, new at this stuff, I really recommend to watch some of my video about allowable stress design versus load resistance factor design. They're two different design methods. One is the older generation, this one is a new one. This one basically over the years they modify things based on probability, and this used to be the older way when the structure was built very strong and oversized, and there's a different theory about it, but I'm not going to get into it. So anyway, okay, so the first thing we're going to go ahead and do, we're going to check the end plate available strength. Let's talk about end plate. We're going to cover a whole couple of lectures on this. Let me bring this up on a screen a little bit. There's a variety of different format of end plate. And you can see these are basically made for like a moment connection, but our end plate is for a shear connection. But never mind. Never way. Either way, they're all the same. It's the plate that is welded to the end of the beam, and is very common and economical, and is easy to use. And they are coming in different shapes. I think I might have a bunch of pictures of some of them done a job I did. Let me see. These are end plate. There's another end plate right there, and they used both for column and beam to girder. One thing I want to tell you that there is a whole chapter, whole book on this. Let me bring it over here. You can see that now. If you go on to AISC website and go to under education, and they got a lot of good stuff. Once you become a member, you can do download a lot of nice material for free, and I highly recommend it. Design Guide 39 End Plane Moment Connection. There's a whole book on this, and it's really very good reading and useful. Anyway, let's get back to our problem. Okay, so we're going to go ahead and figure out the end plate available strength using table 10.4a. Let me show you this. See if I can do this. ASC Manual 16th edition. And then we're going to come into table. If you look at this table, table 10.4a, is for shear end plate connection, and it's available end plate strength. Just look at the column heading. You got number of bolt in a row, beam size, length, bolt diameter, and then we have the end plate thickness of the plate. Our plate is 1/4 inch. Our bolt diameter is 3/4 inch, and we had 3 row. So I'm going to come in down here, 3. That's way down here, 3, and our beam was W18, if you remember. And then we have 3/4 inch bolt. And then when we look at these two heading, let's go back up there. One is the ASD, for 1/4 inch is this first one, and the other one is the load resistance factor. Phi time Rn is 85.9. Rn divided by omega is 57.3. So I'm going to transfer those back in my writing. Okay, that's where they come from. Okay, so we basically said phi time Rn is 85.9, and when we did the load calculation, it became 60 kip, the R right here, and then for allowable stress became 40, so 57.3 over 40. Both design method came out okay, so the end plate available strength checks out okay. Well, just we figured it out from table 10.4a. Make sure you go a couple pages before table 4a and read this section on page, it's a page 10-23, and come down and read right here, table 10.4a, available end plate strength. It says, read that yourself, and it's a lot of good things in there. It says table 10.4a, consider the limit state of the shear yielding shear rupture and block shear rupture of the end plate. So they really went through the whole thing. And when you use any table anytime, go ahead and read the description on pages before to kind of give you better understanding of the table. So now we're going to go ahead and do available shear transfer strength at the bolt holes. Now the shear transfer strength at the bolt holes is the sum of the effective strength of the individual bolt we're going to look at the specification J3.7 and J3.11. Once we know that specification a little bit, then we can move on to table 10.4b and 10.1b. Let me write this down so you can have it. Okay, so now we're gonna, once you read section J3.7, J3.11, I will show you in a minute. We're gonna go to table 10.4b, and we're gonna look at the available bolt shear strength per bolt for 3/4 inch groove 120 with thread not excluded from the shear plane, and also the thread condition is N. Let me show you something in my PowerPoint for a second before we move on there. All right, right here. So this is the shear plane right there, and there's a thread is excluded, and there's a thread is not included. And you can see a thread included. It's in the shear plane. You can see it. And thread is excluded. It's not there. And that's what we're looking at here. So let me close this out and see if I can get the camera going here. You kind of come in and read this section on J3.7 when it talks about tensile strength of bolt, and thread part, and then go to the page read the 11 bearing and tear out strength at the bolt hole. And once you understand that a little bit, kind of give you an idea, we can go to table 10.4b, and 10.4b is right here. Let me get this right. And take a look at the table, understand it. It's a shear end plate connection. At the top you have a 3/4 inch bolt, 7, 8, and 1 inch. And then you have a first row is going to be available bolt shear strength. And then a second part will be available slip resistant. And finally be available tear out and the edge bolt. And then you have one more, it's available bearing and tear out. We're going to look at this. So first we're going to go ahead and look at this one right here, and ours is going to be N and excluded, thread condition N, bolt hole, and design group is 120, and there's the N and there's the excluded, not excluded, so we're going to use N, that's why. And then we're going to go to ASD. It's going to be 11.79 kips, and for roll resistance factor is going to be 17.9. Let me go back to the writing. Okay, so now we have that. We're going to say load resistant factor design feed time RN came out to be 17.9 kips, and allowable stress design Rn divided by omega came out to be 11.9 kip. Okay, so the next one we're going to go ahead and do is the available bearing and tear out strength of the 1/4 inch plate for 3/4 inch bolt. Remember, we're going to use the same table 10.4b. Let me write this down. 10.4b. Some designer, they will use table 10.1b. Be careful. If you use this, make sure you multiply by by 1/4 inch, which is the thickness of your plate, and you should get the same answer. But we can do both. Let's go this way first and go back to this table right here, and I will show you. Let me get the camera going. So we're going back to this. We're going back to this table again right here. Table 10.4b. If you look at the tab, it's available bolt shear strength. We did that. Available slip resistant. We're going to come down, look at the available bearing and tear out strength at the bolt, which is right here. Let me get for 1/4 inch. We're going to have ASD is going to be 8.23, and load resistance factor is going to be 12.3. Now, if you use a table 1b, this table right here, if you use this table, it'd be tear out right there. what was that number I'm looking for? It'll be right here. You're going to use the edge distance of 1.25 inches. Then you have to use these number, but remember this doesn't have a thickness, so you're going to multiply 49.4 times 1/4 inch, 32.9 per 1/4 inch. We end up with the same number of the other table, which was right here. We end up with this one right here. So if we use table 10.4b, this is what we get. However, if we use, let me change color, use Okay, so if we continue with the table 10.1b, we can go for a non-edge bolt with the spacing of equal 3 inches. Our phi times Rn become 22 kips, and our Rn divided by omega becomes 14.26. Now, if we go to table, let me change color so you believe me. If you go to table 10.4b, we will get the same exact result. We get 22 and we get 14.6. Let me just go to the table, show you, change the camera. Okay, this is again table 10.4b. If you come all the way down bottom, and you can see in here it's 1/4 inch, 14.6 and 21.9, and that's what we had before. So basically, when we went to table 4b, you can go through all these individual available slip resistance. I think ours was not a non-slip resistant. And then we have available bearing and tear out. Then we look at the available bearing and tear out, the non-edge, all that. So let me show you something in a PowerPoint here. Right here, the plate is, which is this plate right here, is 1/4 inch thick. And this plate is right here, 1/4 inch thick. It'd be connecting to the girder. The girder plate right here, the web plate is a 0.4. So 0.4 is a lot bigger than 0.25. So we're going to say the plate will control. That means if it's going to fail at the plate, not at the girder, because this is the weaker of the two. So we're going to say the plate's going to control. And let me close this out. And now we're going to go ahead and explore find out what is the minimum transfer strength, minimum available bolt shear strength, which is multiplied by 2. So if I look at the plate right here, I got 2 holes at the bottom right here, 2 holes in the middle, and 2 holes at the top. So we got to look at the strength of each individual of these and then take it from there. So let's continue with that. Okay, so here it is. The minimum of the available bolt shear strength multiplied by 2 rho, because we have 2 rho right here, one here, one here, so that's we multiply by 2 row, and then we're gonna use, we already calculated these number from the table 10.4b up here. Where were they? That wasn't it. Some of them is right there. This is one right here, and we did all these number, so we're gonna use those right here, and we're gonna go ahead and top, middle, and on the bottom, and this one was for the just for the top part. So basically we're doing it for this group right here, and controlling is 24.8 kips for load resistance factor design, and 16.5 for allowable stress design. Either one of these fine. We can, you just go ahead do a load resistance factor design. In this example I show both method, so you have both in your for your knowledge and information. I'm going to go ahead continue with the middle and bottom. I'm just going to write it down. Okay, I wrote this down so I can save time. We did each individual, and we came out with the top, bottom, and middle. And now we're going to take the entire thing. We're going to say the available shear strength transfer at the bolt hole for load resistance factor design is going to be feet time out on the top plus the bottom, middle, and plus the bottom. Right here for the middle we have a is time n minus 2. But if you had a situation that like you had multiple row, like 1, 2, 3, 4, and you had multiple, so where's the middle? So that's where this equation comes in handy. But in here, since we have only 3 row, our middle is going to be our middle, and comes out to be 96.4 kips, which is bigger than our 60 kip when we calculated. And if I do the same thing in allowable stress design, it comes out to 64.1, which is bigger than the shear load from the loading of 40 kip. So this going to pass no problem. That means our plate is strong enough, it's not going to fail. So now we let me go back to the PowerPoint. I'll show you something here. We basically said, okay, we want to check the plate. We did check the plate. We did check the shear of the plate was good. We checked the bolt connection was good. So the next thing we're going to check the weld, these weld right here. Find out if the weld is strong enough, because when this is connecting to the girder, is it going to fail from the weld because of the weld, or is it going to fail because of the plate, or is it going to fail because of the beam, or is it fail because of the web? So we're going to check the weld right now. That's what we're going to do next. Okay, we're going to check the weld section, and we say this using 3/16 of weld. You're the designer, you can change this if you want. And go into table 10.4c. The code says, I will show you in a minute, our beam is a TW is a 0.335, but let's look at the table. I'll explain what I have here. I don't have the camera here. Okay, so we're gonna, here's a table 10.4c. Look at the down here, right down here, minimum beam web thickness 0.2866, and we're gonna use this row, which is the weld we're gonna use is 3/16, not 1/4, 3/16. So if we come back down here, it says your the thickness of your web has to be at least 0.2866, but ours is the beam is a 0.355. So we're going to use that, and then we're going to go ahead, look at the number of the row is a 3 right here. Number of row is a 3 row, and then we're going to come across, length is 8.5. We're going to come across right there for load resistant factor design is at 67.9, for allowable stress design is 45.2. And let's take that back in our writing here. So we're going to come back with those numbers we just had to say load resistant factor design, it was feet time R n equal 67.9 kip just makes it really just bigger than 60. And allowable stress design is Rn divided by phi, and that is equal 45.2, which is bigger than 40. It's okay. That's why I like to check both of them, see how close we come to it. This is pretty close. I don't like it. And that's a 316. 316. This is acceptable, but if I had to design this, I'd probably go to 1/4. I cannot go to 1/4 because the minimum, I don't have minimum thickness. So I had to do. Okay, so let's say it's okay. Alright, so we're going to go ahead and do the cope beam strength, and let me go to the PowerPoint first. We're going to go to the manual part 9, has all this explained, but in order for us to check the web strength of the cope beam, we got to look at the lesser of these stuff: limit state of the structural local buckling, shear yielding, shear rupture, block shear rupture, and some of the effective strength of the individual fastener, which we have done some of that anyway. So let's go to the section 9. See if I can bring the camera up. Okay, section 9, there's a cope beam strength, and let me go to the next page. As you can see, we gotta get some of these dimensions. We already have all this dimension ourselves. We gotta find, we know C, we know DC. We gotta find E, and then we're gonna come back in here, follow the procedure in this chapter, come back down here, and we're gonna find out whether HC, HC divided by C, or less than 1 or bigger than 1, or C divided by D is less than 1 or bigger than 1, and which equation we're going to use, 920A or 920B. So we're going to follow this procedure in this page. Let's go back to the writing. Okay, so what we have here, if you go back to the PowerPoint for a second, we already have these dimensions. We know the DC is 2 inches, C is equal 4 inches, and we're going to give it a setback of about 1/2 inches for connection right there. So what I have right here is we got all this information right here. Our E comes out to 4.5, and then the ratio HC is a D minus DC, came out to 16 inch, and C divided by D comes out to 0.22, and C divided by HC come out to 0.25, and I showed you in a section 9 of the manual. Because of those, we're going to go ahead and see which equation we're going to use. So C over D, it was less than or equal 1, and ours is, yes, it's 0.22. Therefore we're going to use this equation. F is equal 2 times I did that wrong, hold on. F is equal 2 times C divided by D, and this is the equation 920A, which is equal 2 times 0.22, and that's equal 0.444. That's the equation 920A of the manual. And since also C divided by HC is less than 1, then we're going to use equation 919A, and that will give us basically K is equal 2.2 times HC divided by C by power 165. So that comes out to be 2.2 times 16 divided by 4 by power 165. So K comes out to be equal 2.17. We're going to continue and go calculate K1. This is based on a manual. Equal F times K. If that's bigger than 1.61, this is equation 914. And that will be 0.444 times 21.7, which is equal 9.63, and that's bigger than 161. Therefore, we're going to say you're going to use equation 918. Look at the manual on your own, and that equation is lambda P is equal 0.475 times K1 E divided by Fy. E is at 29,000 KSI. We know all that for steel. Divide that by 50 KSI. So lambda P comes out to be 35.5. And 2 lambda P, which would be 2 of that, it's going to be 71. I lied. Yeah, 71. And if we look at in this situation, let me switch back a little bit here. We have lambda P less than lambda less than 2 times lambda P, and if that's the case, we're going to go ahead and use equation 9-11, and the plastic section module Z for cope beam is different. So we're going to say okay, so we're going to go ahead and find this, and this is from the table basically. And let's go to that table, show you that. Okay, if we go to table 9.2b, look at the table tabbing. It says shape. Our is a W, here's my hand. Our is W 18 by 50. And when you come back right here, our DC was 2 inch, right? So we're going to come back, and for 50 is a 42.5. So take a look at this table so you know how you use it. That's a 42.5. So that's where we got the 42.5. Now once we have Z, obviously from steel design 1, you learn how to calculate the plastic moment, which was MP is equal Fy times Z, C in our case, and that was a 50 KSI times 42.5, and that will give us 2,130 kip inch. So if we go to let me change color here for good luck. When we switch table to table 9-2A, same way we're going to find section module C, and that comes out to 23.4 inch. And then MY comes out to be Fy times SSC, and that's a 50 times 23.4, and that's equal 1,170 kip inch. You want to know the difference between plastic section module and elastic section module SEX? I highly recommend. Let me bring this up here. You really should watch one of my videos. This video right here. That video right there says plastic section module. Watch this one, kind of give you an idea. Anyway, let's go back to where we were. So there it is, and now we're going to calculate the MN. Our MN, it's going to be MP minus MP minus My times lambda divided by lambda P minus 1. And this is a equation of 9-11 in the manual. So that's going to be basically equal 2130 minus 2130 minus 117 times 45.1 divided by 35.5 minus 1, and that comes out to be 1,870 kip inch. So our Rn is equal MN divided by E, and MN was 1870, E was 4.5. You see that comes out to 416 kip. Now we have that, we can go ahead and find out if it's going to make it or not. So if I go to load resistant factor design, and that's going to be phi is equal 0.9, and phi times Rn is equal 0.9 times 416, and that's equal 374 kip, which is bigger than our 60 kip. And if I use allowable stress design, and omega for beam is 1.67, Rn divided by omega, and that's going to be 416 divided by 1.67, which give us 249, and that's bigger than 40. So the beam is way strong, no problem there. I mean, that's the web. Next, we're going to check the shear strength. Alright, so next we're going to go ahead and check the shear strength of the beam web, and we're going to go to section J4.2a. Let me bring that up. I already has it open, and that is right here. That's a good section you should really read. And if I can get this, somehow I have a hard time with this. Okay. There's the shear strength, section J2, and it checks the strength of the element in shear. And if you go to the next page and continue look at that, you can have block shear and a lot of good reading here. So please read these, that way you know what we did here. Okay, from there we're gonna have the shear gross cross-sectional area, AGV. That is basically HC times TW, which is equal, we had 16 inch because we took 2 inches out of it, remember? And time 0.355, and that will give us 568. Okay, inch square. And then we have the Rn comes out to be 0.6 Fy AGV, which is basically 0.6 times 50 times 5.68, and that will give us 170 kip. Now we have this, we can go ahead and figure it out in both design. Load resistant factor design, our phi is equal 1, and allowable stress design, omega is 1.5, so phi time Rn is equal basically 170 kip, and that is bigger than 60, pass with flying color, and this one will be Rn divided by omega, which is 170 divided by 1.5, and that'll give us 113, bigger than 40 kips. Checked out. So really, the if we go back all the stuff we just went through, and if you look at your note, the one that controlled the available shear strength, the connection is controlled by the weld of the beam. Remember we did the welding, I said, oh, that's too close. Let me see if I can find it. The weld, where are you? We came back to here, we said the weld. The weld was the one that had the closest one right here, which I was not feel comfortable with it. But this is the one that really controlled, because it's the one that's closest and is the one that has the smallest margin. But otherwise, this connection checks out. Now you know how to do it, and good luck. I hope this video was useful, and have a great day.